In this video we are going to talk about the Maxwell's equations, and there are students actually who get confused in the Maxwell's equations, and I hopefully believe that after watching this video they will never get confused about the Maxwell's equations. There are equations actually, those were given by different persons in the history. Finally, at the end of the day, all the laws were called the Maxwell's equations, but they were different laws before Maxwell. Okay, so let me write the first scenario. Maxwell's equations before Faraday and Maxwell, even though they were not called the Maxwell's equations that time, but let me call them as Maxwell's equations. First one is del dot of E equals rho by epsilon 0. This one was actually the Gauss law of electrostatus. Okay. Second is del dot of B equals 0. This law has no name because it tells us actually about that magnetic monopole does not exist. This equation talks about that thing. Okay, so there is third equation which is actually del cross of E equals 0. This has also no name because later on Faraday added this thing. Faraday added something to it, and we'll talk when Faraday comes into picture. Okay, and fourth is del cross of B equals mu 0 J. This was called the Ampere's law. So these are actually the Maxwell's equations before Maxwell and before Faraday. Okay, now here comes the Faraday into picture. So here comes the Faraday into picture. Let me write the Maxwell's equations after Faraday, and but that was before Maxwell. Okay, Maxwell comes into picture later on. So first one is del dot of E equals rho by epsilon 0. Again, this is actually Gauss law. Then second is del dot of B equals 0. You know, magnetic world does not exist, so this will always remain the same way. Okay, there is no problem, and this also remains the same way. So it remains the same way. So here Faraday did something to this equation. So del cross of E equals minus dou B by dou T. So actually change in the magnetic field creates the electric field, and this minus sign comes into picture because of the Lenz's law. Okay, so this is actually Faraday's law plus Lenz. Okay, and fourth one is del cross of B equals mu 0 J. This is again Ampere's law. Okay, now here comes Maxwell into picture, which who does some change to this law. So I should write Maxwell's equations after Maxwell. So first one is del dot of E equals rho by epsilon 0. This we call as the Gauss law. I'm writing only the differential forms. Later on I'll write the integral forms as well. Del dot of B equals 0. Third is del cross of E equals minus dou B by dou T, because Faraday was always there. Okay, and fourth one is del cross of B equals mu 0 J plus mu 0 epsilon 0 dou E by dou T. So this part was actually added by the Maxwell. So we call this as the Maxwell's correction to Ampere's law. So this is actually the Maxwell's correction to Ampere's law. Now these are actually in the present literature, these four equations are called the Maxwell's equations, And whenever we try to write the Maxwell's equations, when somebody says you that write the Maxwell's equations of electromagnetic waves in the free space, in the dielectric medium, or in the conductor, then we'll be dealing with these. Four equations. Okay, so these are differential forms of like Maxwell's equations. Let me erase this and I'll write now the integral forms of these equations. I hope you understand now. So there are actually these four equations initially, 1, 2, 3, and 4 equations. And they were not called the Maxwell's equations that time, but right now we know these are the Maxwell's equations. Okay, this was the Gauss law and this was the Ampere's law, and this law was talking about, this equation was talking about the magnetic monopole does not exist. And later on Faraday did something to this law, and we know then Faraday came and he only changed this equation to this equation. And so these were Maxwell's equations after Faraday, but before Maxwell. Then Maxwell came into picture. He didn't do anything with these three equations. He added something to Ampere's law. We call this as the Maxwell's correction to Ampere's law. So that becomes the fourth Maxwell's equation. I'll tell you how to write the integral forms of these equations. So using the same method, you can write the integral forms of every Maxwell equation. That would be easy then. So we'll use the divergence theorem and we will use the curl theorem or Stokes theorem. So let me tell you first the divergence theorem, what it says, and then you will be able to apply the divergence theorem here. So divergence theorem says del dot of any vector, actually any vector quantity v. Let me not write the v, let me write some different a. Okay, del dot of a, it should be d tau, it should be volume. That changes to a dot dA, and that's closed surface integral. Okay, this is the divergence theorem. And the curl theorem says del cross of a dot dA equals closed. It changes curl from to dot product, but from surface, this is the surface integral, it changes a dot of dl. Okay, this is the fundamental theorem of curl. Okay, so we are using these two equations to write the integral form of these four equations. Then you will be able to write every equation yourself. So let me write the first one. First one is del dot of E equals rho by epsilon 0. Now see, since we have dot here, we have dot here, we have to take the volume integral on the both sides so that we can use then this equation. Okay, so taking the volume integral on the both sides, del dot of E d tau, it's the volume integral, equals rho d tau by epsilon 0. There is no problem in using it. So using this divergence theorem, we can go from divergence to a dot dA, and this is here this surface integral now. Okay, here this is the line integral, because we're moving from volume to surface by using the divergence theorem. So it becomes closed surface integral E dot dA equals, let me take 1 by epsilon 0 outside, and it's rho d tau. Rho d tau is total charge enclosed, because rho is dq by d tau, charge per unit volume, so which implies dq is rho d tau, taking the integral on the both sides, so it becomes total charge enclosed integral rho d tau. So we can write this part as closed surface integral of E dot dA equals total charge enclosed divided by epsilon 0. So now this is the integral form. Okay, let me enclose it with the brackets. Okay, now see, similarly we are going to this equation, del dot of b equals 0. Let me write it here, del dot of b equals 0. Now since what happened to this part? Okay, so since we have del dot of b again, we are again using this del dot of a. You understand? You have to take volume integral on the both sides. So let's take the volume integral on the both sides. So volume del dot of b d tau equals 0. So which implies again using the divergence term, so volume will go to the surface and b dot of dA equals 0. So this is the integral form of the second equation. Similarly, we will do the third equation is del cross of E equals 0. Del cross of E equals 0. Now since we have here del cross of A is surface integral, so we have to take the surface integral on the both sides. So surface integral del cross of E dot dA, remember the surface must be open, equals 0. So we will use the curl term, fundamental term of curl. So it will become closed line integral E dot of dl equals 0. So this is the integral form. Why it sometimes behave weirdly? Okay, now that will be suffice. Fourth one is Ampere's law, del cross of B equals mu 0 J. Del cross of B equals mu 0 J. Now you tell me yourself whether you take the surface integral on the both sides or volume integral on the both sides. We have to take the surface integral on the both sides. So surface integral, but remember it should be open, okay, not the closed one. So take the surface integral mu 0 J, okay, and dA. Okay, now using the curl term here, so it becomes b dot dl but closed. Line integral b dot of dl. Let me take outside mu 0 J dot of dA. Okay, and we know J dot of dA is current enclosed. Okay, so it's closed line integral b dot of dl equals mu 0 I enclosed, because J is actually di by dA perpendicular, di by dA perpendicular, so which implies di becomes actually J dot of dA perpendicular, taking the integral on the both sides, so it becomes I equals integral J dot of dA perpendicular. So here it becomes I enclosed. So this one is the integral form of the Ampere's law. So whenever you want to convert any differential form into the integral form, use this method. You have to check whether there is divergence involved or there is curl involved. Accordingly, you have to take the volume integral, and accordingly you have to take the surface integral, but take surface integral as the open surface integral, because a closed surface has no boundary, so mathematically right side would be always 0 in curl theorem. Okay, so that's not the point. You should take care. You should take care here. But yeah, that's important. You have to check whether you have divergence involved or the curl involved. Accordingly, take the volume integral, take the surface integral, use divergence term to go from volume to surface, and use curl term to go from cross to from surface to line. Okay, that's very actually simple. When you practice it, you'll get yourself what to do and what not to do. Thank you so much.